Deltech Chem 100, Chem 110, Unit 1, continued scientific notation. Scientific notation is a way of expressing numbers that's different from expressing them in decimal format that most of us are used to, and is useful for expressing all real numbers. It is particularly useful for very large numbers and very small numbers that would otherwise require large amounts of zeros when you actually write them down. It's based on powers of 10, and all numbers are converted to this format, and this is a format for the standard scientific notation, n times 10 to some power x. We call n the coefficient, and the power of 10 we refer to as the exponent of 10 or the power of 10. That is the value x here. And in order to keep it as standard scientific notation, the n, the coefficient, must be between the number 1 and just under 10. So 1, 2, 3.16, 9.99999 are all acceptable, but anything bigger than that, we switch the power of 10 and we use a coefficient that is between 1 and less than 10. X is going to be an integer, so the power of 10 is going to be a positive, negative, whole number, or 0, so that's an integer. We don't typically put non-integers in the power for the standard form of scientific notation. So when you use scientific notation, if you have a power of 10 that's 0 or positive, 0, 1, 2, 3, 4, 5, etc., that represents a large number. So numbers greater than 1 will have 0 or positive exponents, powers of 10. For example, 6,000 is equal to 6 times 10 to the 3. 10 to the 3 is 10 times 10 times 10, or 1,000. Therefore, 6 times 10 to the 3 is really equal to 6 times 1,000, or 6,000. Likewise, if you have small numbers, that is less than 1, these will have negative exponents. For example, 0.06, a number that is less than 1, is represented in scientific notation as 6 times 10 to the minus 2 power. 10 to the minus 2 power is equal to 1 divided by 10 to the 2 power, or 10 squared, and therefore 10 to the minus 2, instead of being equal to 100, is equal to 100th. So 6 times 100th, or 6 times 0.01, is equal to 0.06. Here are examples of scientific notation values: 5 times 10 to the 3, 3.16 times 10 to the minus 4, or 6.02214076 times 10 to the 23. And this last number is actually very important to chemists. This is known as Avogadro's constant, or Avogadro's number, or simply a mole, and we'll talk about that later. So, in order to discuss scientific notation, we have to talk about powers of 10. And we've already briefly talked about a couple different examples of powers of 10, but let's start from the beginning. When the power of 10 is 0, 10 to the 0 is actually equal to 1. In fact, any number raised to the 0 power is equal to the number 1. So 6 times 10 to the 0 would be another way of saying 6 times 1, or simply 6. 10 to the 1 power is equal to 10, and that is because any number raised to the 1 power is equal to that same number. So if I had 5 to the 1 power, that would be 5, 8 to the 1 power, that would be 8, pi to the 1 power would be pi. So as an example, 9 times 10 to the 1 would be the same thing as saying 9 times 10, or 90. If we continue this trend, 10 to the 2, or 10 squared, is equal to 10 times 10. The number tells you how many times to multiply itself, the number by itself. So 10 squared is 10 times 10, or 100. Therefore, if we had a scientific notation value of 3.4 times 10 to the 2, or 3.4 times 10 squared, that's the same as saying 3.4 times 100, or 340. And you notice that the 3 is in the hundredths place, and then any digits after the 3 just follow it in the number. So we started with 3.4, we put the 3 in the hundredths place, and we just continue writing a 4, and if there are any other spaces necessary to be filled, we fill them with zeros. 1,000 is 10 to the 3, 10 times 10 times 10. So 7.2 times 10 to the 3 would be 7.2 thousand, or 7,200. The note that the 7 is sitting in the thousands place, and the 2 just follows it. 1 million would be 10 to the 6. And you'll notice that in each of these cases, with powers of 10 that are 0 or positive, the value of the power of 10 is simply a 1 with that number of zeros following it. So 10 to the 0 power, 10 to the 0, is simply 1 with no zeros, or 1. 10 to the 1 power is 1 with 1 zero. 10 to the 6 power is 1 with 6 zeros, or a million. So in an example, 2.34 times 10 to the 6, that's the same as saying 2.34 million, or 2,340,000 as a total number. Now, you'll notice the 2 is sitting in the millions place, and it's just followed by the 3 and 4 in the same order as in the scientific notation coefficient. And we can continue on to 9, and you see 9 is 10 to the 9 powers is a billion, 10 to the 12 would be a trillion, etc., etc. So 6.05 times 10 to the 9 is 6.05 billion, or 6 billion 50 million. Now we can also go to negative numbers. We'll start again at 10 to the 0, which is 1. So 7.33 times 10 to the 0 is simply 7.33. But if we have powers of 10 that are negative, now we move the decimal place to the other side of the 1. And so 10 to the minus 1 is 0.1. Now you notice you can't use the same rule of counting zeros as you did with the positive numbers above. So when you see 10 to the minus 1, that tells you that the 1 is in the first decimal place after the decimal. So 2 times 10 to the minus 1 is the same thing as saying 2 times 0.1, or 0.2. 10 to the minus 2 is 100th, as opposed to 10 to the 2, which is 100. So everything is inverted at this point. 0.01 is represented by 10 to the minus 2. So 3 times 10 to the minus 2 is 0.03. Note the 3 is starting in the second decimal place after the decimal. So with negative numbers, you merely look at the coefficient, and then you look at the power of 10, and you place the coefficient starting in the decimal place represented by the positive version of the coefficient. So 10 to the minus 2 says that that 3 will start at the second position. 10 to the minus 3 is 1,000th, or 0.001. So 4.32 times 10 to the minus 3 is 0.00432. So find where the 4 goes. That will be the third decimal place, and then just follow it with the remaining digits, 32. 10 to the minus 6 is a millionth. So 7.00 times 10 to the minus 6 is 0.000007, and since we started with 2 zeros in the scientific notation, we put those zeros in the decimal. And this will come up later when we talk about significant digits, but I will tell you now that all digits in the coefficient of any scientific notation number are considered significant, whether they're 0 or not. So in this case, 7.00 in the scientific notation, all 3 of those digits are significant, and therefore we show all three digits in the decimal format on the right. 10 to the minus 9 is 1 billionth. So 1.302 times 10 to the minus 9 would be 1302, but start the 1 in the 9th decimal place. So it's 0.00000001,302. So it's very easy to create scientific notation format from a decimal number. Somebody gives you a decimal number, you look where the decimal is, and you merely move it until the decimal place forces that number to be a value between 1 and just under 10. So 5 is between 1 and 10, but not 10. And therefore, we move the decimal place 2 places. We artificially make this number smaller by 2 powers of 10. So we have to fix that by multiplying it back by the 2 powers of 10. So our number, instead of being 500, it becomes 5 times 10 to the 2, because we moved the decimal place 2 times in the movement from 500 to 5, and therefore we have to compensate by putting the 10 to the 2 back in there. Now, you will notice that 10 to the 2 is a positive number. It's a number 0 or greater, and therefore that tells you that if you looked at 5 times 10 to the 2, you would know that 5 times 10 to the 2 is greater than the number 1. If you have a power of 10 that is 0 or a positive number, your value, your whole value, will be greater than 1. And sure enough, 500 is greater than 1. Our next number, 2.087, well, there, 2.087 is already between 1 and 10. There's no need to move the decimal, so we just multiply it by 10 to the 0, which is the same thing as multiplying it by 1. We have moved the decimal place 0 times. 98,760, we look where the decimal is. We have to move that a total of 4 times, and therefore, to get that 9.876 value, we needed to move it 4 times. Therefore, we multiply it by 10 to the 4 power to compensate for that. Now, you'll notice we did not include the 0 here, and that is because this 0 is not considered significant, and we'll talk about those rules later. Then we have 0.465. Here's a number less than 1, so you already know that whatever power of 10 you have, it will be a negative value. So look where the decimal place is. We now have to move the decimal place to the right. We have to make the number artificially bigger to 4.65. And we've moved it to the right by 1 power, so therefore we need to compensate the 4.65 by multiplying it by a small number, 10 to the minus 1. Notice in each example, if the number was greater than 1 to start with, then you will have an exponent that is 0 or positive, and if you start with a number that is less than 1, you will end up with a negative exponent. So in this case, we move the decimal place to the right 4 times. We're artificially making it larger by 4 powers of 10. Well, we have to compensate that by multiplying it by 10 to the minus 4 to make it small again. And you end up with 1.306 times 10 to the minus 4. In every case, you're going to look for the first digit in the number that is significant, meaning not 0 and significant. And there are some zeros that are significant, but in this case, the first digit will not be a 0. You look for the first non-zero digit, you move the decimal place there, and then it's multiplied by a power of 10 that represents how many times you shifted the decimal place. So to convert standard scientific notation, here's an example, 9,000. We move the decimal place from 9,000 three orders of magnitude, or 3 powers of 10, to make it just 9, and we have to multiply it by 10 to the 3. 0.1 would be moved 1 time, but to the right, and therefore it would be 1 times 10 to the minus 1. 0.008 is 8. We know the first digit is 8. There are no more digits after the 8. So it's 8 times what power? Well, notice that the 8 is sitting in the third decimal place. Therefore, it's 8 times 10 to the minus 3. When you have a large number, look where the first digit is and count how many decimal places are to the right of that number. So 5 is followed by 6 decimal places that are all still to the left of the decimal place. The decimal place is not written here, but you still have 6 digits between the 5 and the decimal place. Therefore, it's 5 times 10 to the 6, but since it's 5,700,000, we include it as 5.7 times 10 to the 6. Here's a number, 100,001. The decimal place would be to the right of this whole number, and therefore we'd have to move it 5 times in order to get 1.00001, and therefore we multiply that by 10 to the 5th power. Every time you have a large number, meaning greater than 1, your power of 10 is 0 or positive, and if it's a small number, meaning less than 1, your power of 10 will be a negative number. If you look at this number, you can see immediately you're going to have a negative power. You see that the 5 is sitting in the 4th decimal place, so you already know the power of 10 is minus 4. Therefore, it's just a matter of putting a decimal place between the first non-zero number and whatever's next, in this case it's the 6, and rewriting it. So it's 5.622 times 10 to the minus 4. And I'll leave these to you for practice. You can see that you're just moving the decimal place and compensating by the powers of 10. If we do the other way around, so we're starting with scientific notation and we're writing the standard decimal format of the number, let's look at the first one. We have 4 times 10 to the 3. Well, you can look at this a number of ways. This tells you, oh, I'm going to move the decimal place 3 times to make 4 a bigger number because 10 to the 3 is large. Or you can say, oh, it's 4 times 10 to the 3, that's the same as 4 times 1,000 or 4,000. So you can do this a couple different ways, whatever strategy works for you. 3 times 10 to the minus 1 tells you, okay, it's less than 1, and the 3 will be in the first decimal place after the first place after the decimal. So it's 0.3. 6.5 times 10 to the minus 3 tells you the 6 will be in the third decimal place and that this number will be a small number, less than 1. That would be 0.0065. 6 is sitting in the third decimal place, and we just follow it with whatever digits are after the 6. In this case, it's just the 5. Likewise, our next example, 5.26 times 10 to the minus 5, this tells you that you're going to be writing a 0.00 whatever, and that you're going to start writing your 526 at the 5th decimal place because it says 10 to the minus 5. Here we have a very large number, 1.9673 times 10 to the 8. This tells you that the 1 will be followed by 8 decimal places before you hit the decimal. So at this point, you just write 1, and as you're writing 9673, you start counting. You should have 8 spaces. Now you'll notice 9673 takes care of 4 of those spaces. The rest of those spaces need to be filled with zeros. And the rest of these you can do on your own as practice. 9.0100. Don't forget to write those extra 2 zeros at the end. They are considered significant. All scientific notation coefficient digits are significant. Not necessarily with decimal, but all that are written in scientific notation are. So I'll just toggle through these and you can practice these on your own with the PowerPoint presentation. Now here are some example problems to practice on your calculator. Everybody's calculator is different, and I highly recommend you review the instructions on using your calculator. Some of you still have your instructions, some of you don't. You can always look up instructions for your calculator on the internet, or you can come and talk to me or one of the tutors. I'm sure we can help you figure out how your particular calculator works. But I will tell you this. I will tell you that on most calculators, to input a scientific notation number, it's one of a couple different ways, and I'm going to switch over to an annotate mode here so that I can write. And if we look at this very first number here, if you wanted to input this in most calculators, you would write 5.67. You type that into your calculator, and then you'd hit a button that looks like this. EE. Some calculators, this button will say EXP. And what this button means is times 10 to the something power. So you do not need to hit times. You do not need to hit 10, and you certainly don't need to use the 10 to the x button. Please don't ever use the 10 to the x button for inputting scientific notation. It will work sometimes, like in the second problem here, but it will not work in other times, like the first and third problem here. So please do not use the 10 to the x button for exponents in scientific notation. Use one of these two buttons depending on your calculator. And then you will put in your exponent. Well, in this case, the exponent is a 3. And then this would be represented on your calculator. It's the representation of this number, but it will appear, depending on your calculator, once you've typed it in, your number will actually look like this, depending on your calculator. It will look like 5.67. Some calculators will have a little e, and then it will have the number 3, or maybe there's 0 before the 3. And this is the way the calculator, it's also the way Excel represents numbers that are in scientific notation. This literally means 5.67 times 10 to the 3 power. Some calculators will represent this as 5.67 and just have a space and have the 3 over here, or occasionally we'll have a 0 over here. So be careful when you're reading your calculator how these are being displayed. There is one caveat here for inputting numbers that involve negative exponents, and I'm going to erase all of this actually and start again with the, whoops, I'm sorry. Let's get rid of that. And we'll go back and we'll write this number right here, 3.02 times 10 to the minus 8. So you're going to type in 3.02 in your calculator. You're going to hit the EXP or the EE button, depending on your calculator. And some calculators require you to put the negative sign in first, but do not use the minus sign on your calculator to do this. Your calculator should have a button that looks like one of two things. So the EE button could also be an EXP button, and pardon my penmanship here. This could look like a plus/minus button. On some of the fancier calculators, it will say CHS. That means change sign. In other words, change it from positive to negative, or change it from negative to positive. And then you would type in the 8. And this would tell the calculator that you mean 3.02. This button means times 10 to the something. This means negative, and this, of course, means 8. And that's how you represent it. And your calculator might display it as 3.02 with a space, E, and maybe minus 8. It might say E minus 08. It might say no, it might have no E at all and just say minus 8, or it have no E at all and say minus 0.8. But in each case, it'll say 3.2 first. And this is the way a calculator represents scientific notation. So when the calculator gives you that, you would rewrite it on a test or a problem set or a lab as 3.02 times 10 to the minus 8. And I will tell you, if you don't want to type that on some assignment, it is perfectly acceptable to write 3.02 little e minus 8. And most people that deal with numbers, especially with spreadsheet programs, will often write scientific notation in this format, but when you're learning it, this is the format you should be writing it in. If you have to input it into a computer, that is typically the way you would input it, say if you were working in Excel, for instance. So I'm going to erase all of these notes here, and we'll discuss a couple more functions on the calculator, the log button and the power of 10 button. So this is the one time you do use the 10 to the x button. And this is the time you're going to use the log button, the LOG button. Sometimes it's written as LOG sub 10. This is called the base 10 logarithm. And different calculators do different things. Some calculators, you type this number in first, the way we just discussed. then you hit the log button, then you hit the change sign button. So you would put your number in first, your log button tap second, and then you'd hit your plus minus or your change sign button. That's on some calculators. On the more programmable calculators and fancier calculators, you do it the other way around. You change the sign first, you tell it you're going to take the log of something, and these are the calculators that actually display the entire equation on the calculator screen. And then you would type in your number. So in this case, we would put in 3.02. We would hit the EE button. We would hit the change sign button again to change it to a negative, and then we type in 8. And then you hit equals, and you would get the value for that equation there. Now this equation here, 10 to the minus 9.3 power, this is where you're going to use your 10 to the x button. And again, different calculators do different things. On some of the simpler calculators, including the ones on iPhones, for instance, you would type in your number negative 9.3 first. So you'd hit the change sign button. You'd hit 9.23. So now the calculator thinks it's minus 9.23. And then you would hit the 10 to the x button. Well, the problem is there is no separate button for 10 to the x. What you really will end up doing is looking above this button, the log button, or the log base 10 or the log button. Above that button, you'll see a little thing that says 10 to the x. And the way you get that is you press the second button, which is typically in the top left corner of your calculator, and then you hit the log button. And that is basically telling your calculator, don't use the log, use the function written above the log, which is the 10 to the x function. So you change the sign to negative, you type in your number, and you represent this button by hitting second and then the log button that it's actually attached to. In other calculators, it's again the opposite. You would type in the 10 to the x button first, and the way you get the 10 to the x button is the way I just described. It's really equal to the second button, and you hold these two buttons together, by the way, at the same time. Second button and the log button. So you're going to be touching these together in some calculators, and some you would hit second first and then log. Check your calculator. Most of the time it's sequential. Hit the second, then hit the log. That means 10 to the power button. And then you would type plus or minus button, and then you type the 9.23. And then you'll hit the equal sign and you'll get your answer. So this is how you input the data in most calculators. I've shown you a couple different versions. Hopefully your calculator will do one of these, so please practice. Now, how do you know you got the right ones? Well, the way you know you got the right answers is because I have given you the right answers, and you'll notice for some of these numbers I've given them to you in both the scientific notation format and the decimal format. Why did I do that? Well, in a lot of calculators, if you're typing in scientific notation, they will frequently automatically convert to the decimal format if it can fit on the calculator screen. This number is far too small to fit on the screen. This number is far too big to fit on the screen. This number is usually small enough to fit on the screen. So you will see it displayed this way. So be aware that your calculator will switch back and forth. And some calculators have methods of switching back and forth, and it depends on the calculator. You will have to look for the button. Some you will see something that has a F and maybe a couple arrows and another notation here. It might be an S, it might be an N. A lot calculators do different notation. Let's just call it N for now. But what this means is it switches between floating decimal, which is this format, and scientific notation. Now, not all calculators use N. They may use a different letter. It might be an S, it might be an N, it might be a totally different letter. You have to check your own calculator. But this will flop back and forth between scientific notation and decimal format. It's a very useful function, especially when you need to figure out what the number actually means. So at this point, we're going to stop this unit and we'll return to the next unit on the next video on measurements.